And we'll go from the current slide. And I'll even turn on the projector for you. Started the first class this morning with 0 students, but so I didn't have the projector on. Then they started coming in, wound up with perfect attendance. Of course, it was only 4 like this class, but okay, 3 out of 4 are here now. If Rodney shows up, we'll have perfect attendance today too. And evidently, by a question I had as my last class was leaving, they seemed to be surprised by this because I said, we'll see you Monday. They said, we don't have class on President's Day, do we? Yes, we do. Okay, that's not a 2-year college system holiday.
That's right, it sure is President's Day Monday.
Yeah, but K-12 is off then, I think, most schools, but the 2-year and most 4-year schools I don't think take President's Day off. I think that the story behind it was back when they made Martin Luther King Day a federal holiday in order to keep the same number of holidays for the 2- and 4-year schools, because we had to meet certain days. You know, they decided to, since it was so close to President's Day, they'd lose President's Day. Now, the K-12, they don't come in the summer, so they don't have to worry about it. So they still take it off, I think. Most of them do anyway. Okay. Now, any questions on anything we've done so far? Everybody here got the test, right? Chapter 2 test. Gave it to you a little early before we finished the chapter because most of the questions on there you wouldn't have to have this last little bit to do. Okay. So, no questions. Where we pick up today is page 107 if you got the text. It's section 2.9, last section in chapter 2, proving the limit theorems. In practice, the formal definition of a limit is rarely used to evaluate limits. Emphasis placed there. Okay? Most of the time, you plug it in, use the basic limit laws, squeeze theorem, but most of the time, the formal definition you don't necessarily do. However, the formal definition allows us to prove that these laws are rigorous in a rigorous fashion and thereby ensure that calculus is built on a solid foundation. And I know you all had doubts that it was, right? Okay. So you wanted to be convinced of that. We illustrate by proving the sum law. And now, I know one of you's a math major. How about the other 2? No? No, yeah, y'all are, one of you's, yeah. So you probably aren't as concerned with proofs as math majors may be. And are you planning to stay in math major or change to something else when you go to a 4-year school?
Well, I'm math right now, but I'm planning on transferring into an electrical engineering degree.
Oh, okay.
So all my credits will transfer.
Right, yeah, okay. So you probably won't be as concerned with proofs either, but still not a bad exercise to do, okay? Now, here's how you begin this. We're not going to do it in gory detail, but we will at least hit a few high points. So here's what we assume, and I think I've got to get, because I'm going to write, I have to squeeze back down. Okay. Let's assume that the limit as x approaches c of f of x is equal to L. Okay? Now, we'll also assume, because these are for the sum law, these were the assumptions, that the limit as x approaches c, same c, of g of x was m. What we are trying to prove, these are the givens, okay, and this is the proof. If those 2 are true, we're trying to show that this is true, that the limit as x approaches c of f of x plus g of x is equal to L plus M. Now, it makes perfect sense, okay? But now they have this little thing, and if you had been doing lots of math proofs, it's called the triangle inequality, okay? And that goes something like this. If the absolute value of A plus B, okay? Now think about that for a minute. If both A and B are positive numbers, then the sum's a positive number. The absolute value is exactly its value, right? But if, let's say, and same thing sort of is true for if both of them were negative. If A is negative and B is negative, you add them together, you get a bigger negative number, but the absolute value is positive, and it's the same value. But then let's think of the case where if one of these was positive and one negative, doesn't matter which. Okay, you could do it for both if you wanted to. So let's say A was negative and B was positive. Then the sum of A and B is going to be something less than the absolute value of A plus the absolute value of B, right? Because a negative number plus a positive number is going to actually reduce one of those, okay? If the positive number was bigger, the sum is going to be a smaller positive number. If the negative number were bigger, then it's going to be a larger negative number, but this absolute value would be less. So that leads to what we call the triangle inequality, that the sum of A plus B is always less than or equal to the absolute value of A plus the absolute value of B. That's called the triangle inequality. Not exactly sure why. It kind of little bit smacks of the Pythagorean theorem because it doesn't have any squares in it. But we know that the hypotenuse is the square of the hypotenuse is equal to the sum of the square of the other two. But generally, the hypotenuse is less than the sum of the other two. Okay, the squares are equal, but not the other. Well, this kind of says the same type of thing, only different. Okay, the absolute value of this is less than the sum of the absolute value. Less than or equal to. Could be equal to if either both A or both B are either positive or negative. Okay, but if one's positive and the other negative, then that would be less. Okay, so we're going to use that. Okay, and I don't know if you recall, but what this implies, remember, and this is given. We know it's true, so we know the absolute value of f of x minus L, okay? And it really doesn't matter which way you do it. They put it this way, I think. That's used in the proof of that, right? You know, it's less than epsilon. You know, that's how you go about doing it. So let's take this value here, but we're not even going to deal with the absolute value. I don't know why. I think they should, but we're just going to take that quantity and say that's equal to A. Okay? That's how much alpha of x differs from L. Okay? For x not equal to C, that difference is your A. And we'll do a very similar thing here. G of x minus M, we're going to set equal to B in this triangle inequality. Okay? Now, here's why. To prove this limit, okay, we go to this thing down here. I know it's hard to see. I'm debating on whether I ought to zoom in on it or not. I think I will. Okay, and then I may. Let me see if I can get this in the same field of vision. Not quite, but close. Yeah. Okay. What we're trying to prove, the limit as x approaches c of f of x plus g of x equal L plus M. That's the sum rule, okay? So what we're looking at then is the absolute value of this thing, f of x plus g of x, minus this thing, L plus M. And what we're using the triangle inequality for is to say that's less than this difference, absolute value of that, plus that difference, our triangle inequality. It's just you're grouping these two. I forget, you can't write on this after you've blown it up. So let me shrink it down again. This is what we're trying to show, and what we've done is group these two together and put them here. That's like your A. And group these two together and put them here. That's like your B here. And by the triangle inequality, the absolute value of the whole thing, A plus B, has to be less than or equal to the absolute value of A, which was this one, okay, plus the absolute value of B, which was this one, okay? But since we already know this is arbitrarily small and that's arbitrarily small because we know these limits exist, okay? That means that this is 2. And what you would use for this limit would be an epsilon, you call this epsilon 1, this epsilon 2, and your epsilon here would be epsilon 1 plus epsilon 2. There would be your epsilon greater than 0 such that, and you could go on and prove the whole thing. Now they do epsilon over 2. That's fine too. You can choose it however you want to choose it, but make that less than epsilon, okay? I think that's the only slide they show. No, they take it one more. Now, again, let me go back then. They did this epsilon over 2 and this epsilon over 2, okay? So your epsilon would be epsilon over 2 plus epsilon over 2, and that would be the epsilon for this one, okay? And that's what they do here. I'll blow this one up. Boom, I blew it up. Okay. This thing here, which is the left-hand side we had before, and we knew because the limits existed from what we had on the last slide, and that was some epsilon over 2, this one, F minus L, and G minus M was epsilon over 2 here. The sum of those is epsilon. You've shown this is less than epsilon whenever 0 is less than absolute value. That was your formal definition of your limit. If you can show this, you prove the limit. We just have for the sum formula. Now this is a quick and dirty, blah, blah, blah. Read the text. It'll go through a little more detail. Any questions, or do you care? Okay. No on both counts? Okay. Let's now, if not, do your preliminary questions. Do y'all find these helpful? Okay, let's do it. Okay. Given that, this is preliminary question 1, 2.9, page 108. Given that the limit as x approaches 0 of cosine x is equal to 1. And we all buy that, right? As cosine gets close, x gets closer and closer to 0, cosine is going closer and closer to 1. You know that, right? Okay. Nothing new there. Which of the following statements is true? A. If absolute value of cosine x minus 1 is very small. Do all of you have your books? No, you don't have yours today. Okay. Is very small. I was going to say, I'll let you read it and I won't have to write this down. Then x is close to 0. Okay? Is that true? Is that necessarily true just based on this? If cosine x minus 1, the absolute value of that, is very small, then you know that x has to be close to 0. Yay or nay?
I mean, the only part that kind of throws me off is very small.
Yeah.
Because if we're still plugging in 0 for cosine of x, that's 1 minus 1, right?
Right.
So, I mean, it is close to 0 because it is 0.
Okay.
So it's no then.
Second?
So it's no, right?
It's not right. Okay.
Like the answer is no, right? Because if you minus 1 is zero, how much closer can you get when you get to 0?
Okay, so y'all agree that statement's true. Okay? All right. I want you to plug in x equal pi. And what will that give you? No, that won't work as well. Let's do 2 pi. Let's do 2 pi.
So 6. So it'd be 5 something. That's
No.
the value of.
Well, cosine of 2 pi is what?
Oh. Will that still be 1?
That'd still be 1. Okay? And absolute value of cosine 2 pi minus 1 is very small. 0.
Okay.
Does that mean that x is close to 0? No, x is 2 pi. That's not very close to 0,
okay.
is it?
Gotcha.
Right.
Okay.
So no, just because one way works doesn't mean the other way works.
Gotcha.
Okay.
I thought that we were. See, I was reading it. Given the limit, I was reading what was.
Yeah.
In the top.
Yeah.
So given that limit, cosine x as x approaches 0 is equal to 1.
Yeah.
Which would fall. But that makes sense.
Yeah. Okay. So A doesn't necessarily follow. B, there is an epsilon greater than 0. Okay. Such that, I usually use a colon or lines or stuff like that, means such that. If, I don't know why there's 2 ifs in there. If 0
Is less than the absolute value of cosine x minus 1.
okay,
Is less
and that's less than epsilon. Okay.
Then the absolute value of x is less than 10 to the negative fifth.
Less than or equal to or less than? Less than 10 to the minus 5. Okay. That there is an epsilon greater than 0 such that if 0 is less than absolute value of cosine x minus 1 less than epsilon, then x is less than 10 to the minus 5.
So are we looking for the value of epsilon or x?
That's what I was trying to puzzle with. Because that limit does say that, well, I mean, basically you use the same 2 pi as you did before. Okay? For arbitrarily small x's, epsilons, absolute value of cosine 2 pi minus 1 is very small.
That's right, because that's what we were talking about was if
So x doesn't have to be less than,
if you took the absolute value of something but you're subtracting something within the absolute value, it's going to be less than the absolute value of adding them both together. So,
yeah, but this is a triangle inequality. I mean, you could say that, but the thing is, again, you could put in x equal 2 pi and that wouldn't be true. This part would be true. If x equals 2 pi here, then yeah, you can get arbitrarily small.
Right.
Okay? But x doesn't have to be, 2 pi is not less than 10 to the minus 5. Right. Again, it's almost the same thing as the last one was. So that one's not necessarily true. I can see what you say. Are these any good? No, I'm sorry. You didn't say that, did you? C. There is a delta greater than 0
such that
such that
if
if
0 is less
0 is less than
than the absolute value of x.
minus c, or minus 1, minus what?
Oh, no, just the absolute.
Absolute value of x. X minus 0 is x. Okay, that's what they're doing. Your c is 0, so all right. Saying the same thing. Okay, absolute value of
That's less
okay.
than, is that gamma?
That's delta.
Delta.
Delta. Okay.
Then the absolute value of cosine x minus 1 is less than 10 to the negative fifth.
Okay. There is a delta greater than 0 such that if 0 is less than absolute value of x is less than delta. So there is a delta somewhere out there. You can make that be true. Yes, that is true. You can pick a small enough delta to give you, make this between, well, wait a minute. Yeah. Going that way, that does work. See, yes, that basically is the formal definition. Okay? You can find the delta small enough to make that true. Okay? Let's see about the yeah. Yeah, that's a lowercase delta. That's the uppercase delta. Yeah. What's that? Okay. It's just like the English alphabet, capital delta, lowercase delta. It's just that here we're using lowercase epsilon. Uppercase epsilon doesn't look like that either. No, those are just symbols like X. Or, yeah, they're representing small values. Okay, that's all it is. It's not a specific value. It's just representing. The delta represents how far you are off the C. In this case, it's 0, and your epsilon is how far you are off your limit, the f of x as x approaches c. So it's just giving, they use those, that's, my guess is that's what the first guy who did it said, well, let's use epsilon and delta. And so everybody's used it ever since, okay. They're just representing small values. Okay. All right, D. There is a delta, boy, that's starting off the same, greater than 0, such that if
0 is less than the absolute.
Okay.
0 is less than the absolute value of x minus 1.
Okay, so that's not the same. Okay. Let me get back. Yeah. Okay. If 0 is less than absolute value of
X minus 1, that is also less than delta.
okay.
Then the absolute value of cosine x is less than 10 to the fifth. 10 to the negative fifth.
Okay. What you think about that one? Yay or nay?
I'm gonna say nay because the other one.
The other one was yay. Yeah,
Yeah,
got
I
it.
mean, but,
All right, you can only cheer for one. Okay,
Yeah.
so he's only going to cheer for 3. Yay, 3. Okay, C. Now this is wrong. It's wrong because the delta refers to difference with x. What you've done here is do the x minus the limit. X refers to the c. Cosine x, the function, refers to the limit. That's just wrong. Okay, x is approaching 1. It's cosine x approaching 1. X is approaching 0. And here you have cosine x has the value of that would be cosine x minus 0. You got the things backwards. Okay? This is correct. That one's wacko. Okay? Because it doesn't even make sense. As x is approaching 1, now x minus 1, in other words, x is approaching 1 here, right? If x is approaching 1, do a cosine of 1. It's not going to be less than 10 to the minus 15. No way. So, yeah, that makes no sense at all. So the one that makes sense is C. They better have that in the back or else we go up very angry, okay? 2.9 preliminary questions. C, they got it right. Good for them. Okay. All right, that was number 1. Let me erase all this. Is that okay? All right, and go to number 2. They only have 2. That's sort of refreshing, isn't it? Well, let's see. It's 4 parts to that. Suppose that it is known that for a given epsilon and delta, okay, if 0 is less than absolute value of x minus 3, that's less than delta, that's making sense, then the absolute value of f of x minus 2 is less than epsilon. Okay? Which of the following statements must also be true? Okay. Suppose it's known for a given epsilon and delta if the difference between x and 3, in other words, is x is approaching 3 closely enough that it's less than delta, then the absolute value of f and 2, in other words, f of x is approaching 2 within the limits of epsilon. Which of the following must be true? A says that if 0 is less than absolute value of x minus 3, less than 2 delta,
The absolute value of f of x minus 2, and absolute value is less than 2 epsilon.
now A is just epsilon, isn't it?
Oh, it's using the opposite.
Yeah, you jump down to B. Okay. Now, I would say on this one, not necessarily. Because what the top one says, if you're within delta units, one side or the other of the value 3, that then your function up here is within epsilon units of 2. Okay? If you double this one, you're not guaranteed you're going to stay within there. That may get a little bigger. It may be. Maybe it still will work, but in general it won't. Okay? You can't guarantee that. So that's not necessarily true. Is that making sense? Okay. Now, the B part. And, I mean, let's just go back quickly. Oops, here it is. Here. This is what we're saying here. What was x and 3? So this was your 3. As x, if x is within delta units of 3, what the first thing, what the given there said, you're guaranteed to be within epsilon units of f. 2, I believe it was, wasn't it? Okay. Now, if you double this and make it 2 delta, that doesn't necessarily mean you're still going to be within epsilon up there. Okay. So that one's not necessarily true. It could be, but in general, you can't say it would always be true. Oops. Okay. So let's look at B. If this part is the same, but now it's delta,
And then 2 epsilon. That's only
and this part would be the same, and is that less than 2 epsilon? Okay. Yeah.
because
If you
it's the
if you
same.
don't, yeah, if the first is true, if you're within epsilon of delta, that guarantees you're within, within delta of x equal 3, that guarantees you're going to be within epsilon of x equal x, f of x equal 2. So if you keep the delta the same, double that's why you're guaranteed, yeah, you're still within that. Okay, so yeah, B's got to be true. Okay, C. Is that making sense?
A little bit.
Okay,
So
let's go.
basically with B, are you saying that since we kept the continuity of the, well,
No, let's go back here.
changed-
This picture here.
Sorry.
If you keep the delta here, but do 2 epsilon, if it was true that with delta, you're within delta units of 3 here, that you're going to be within epsilon units of 2 up here, f of x equal 2, then if you keep the f delta the same and expand the SEI, you're certainly still going to be within that. So if this is true, then certainly going to be true that that is true. Okay, if you double the epsilon. So that's, since they have that picture there, let's use it. Let's see what C says.
So is delta the x?
Delta is the tolerance around x. Maybe you're not going to have x exactly equal to 3, but you're going to have it close. Pretty close, okay? And if you're within that here, it guarantees you're within epsilon here. That's what the first thing says.
Gotcha.
Okay, so if you double this, you're not necessarily going to be within that. But if you keep this the same, you're definitely going to be within double this.
So delta's the tolerance of the x, and
And
epsilon's
it's a tolerance for the y or the f of x.
Gotcha.
Exactly. Okay. So let's see what C says. If 0 is less than blah, blah, blah.
Delta over 2.
Okay. So this part's the same, and this is less than delta over 2. Does that imply
And then epsilon over 2.
that absolute value of f of x, I should have just put it equal, is less than or equal to epsilon over 2. There's a part of me that thinks, I don't think you can necessarily say that. Let's go back and look at our picture again. If this was a rapidly changing function here, and delta over 2 here, if that's going up at a rate faster than this, you may not be within epsilon over 2, I think. If that's, this one's almost linear here, not quite close, and almost 1 to 1. If that was really steep here, and you have this, I'm not absolutely certain you would still be within half of epsilon. It could be, but I don't know if it's guaranteed to be, because they are not linearly related, I don't think. Okay, so I'm going to hold judgment on that one. This one is a not necessarily, and I'll put not necessarily. This is true. I think this is not necessarily 2, but I'm not as sure about it. Okay, let's see what the D one is, because you could have more than one of these right. If all this is the same, including the delta over 2, then that implies all this is the same, but it's less than epsilon. Okay? That one, just like B, I think has to be. Because you see what you're saying is your given here is that the delta guarantees you within epsilon. If you're within delta here, you're within epsilon. So if you get within delta over 2, you're surely still within epsilon. It's just like keeping delta the same and doubling epsilon. This is having it delta over 9. But the previous one, if your curve was doing something kind of really weird in there, very steep there, having the epsilon wouldn't necessarily allow you to have to, having the delta wouldn't necessarily allow you to have the epsilon as well. Okay? They're not necessarily linearly related. So let's see what they say in the back. B and D are true. Good for them. Okay. We got B and D true. The other two were not necessarily true. All right. Done. Okay. Homework exercises. What you've been waiting for. Any of the odds. Wow. I think we went over these before, most of them. Any of the odds 1 through 17, and I would do several of those, not just one or something like that. Okay, some of each type that you might run into. then any of the odds 19 to 23, and then wind up with any of the odds 25 to 29. Now, further insights, I usually take a look at these just to see if there might be something that you might want to choose as a paper topic. I don't see anything particularly, but if you do, go for it. If you need some more practice problems, the review exercises are pretty good. 1 or 3. I don't think you would need to do both of them, but you could do both if you wanted to. Any of the odds 5 through 9. Any of the odds 11 through 49. There's a whole bunch to choose from there. Do just a few and see if you got to grasp the idea well enough. You should. Any of the odds 51 through 57. Okay. Any of the odds 59 through 63. Any of the odds 65 through 79. And I'll let you choose which of those you want to focus on. All right. Any questions on Chapter 2? We finished Chapter 2 now. That means technically, the test is due in a week. If you finish it sooner, I'll take it. If you finish it now, I'll take it. If you need more time, you can have it. But just don't string it out too long. I don't want you to still have the first test out when I give out the second test, okay? And the main reason for that is you need to see if you're missing anything in Chapter 2. You need to find that out early in Chapter 3. So get me the test back so I can get it graded and you can see it. And I need all of you to get the test back so I can return them to you as well. I can let you see them, but I can't return them as long as there's a test out. So don't cheat your classmates from their opportunity to have the test back. Get them in as soon as you can. But don't sweat the next week. If you need more time, take it, but get it done as soon as you can. All right, we finished Chapter 2. If there are no more questions. So what we're going to do now is go to Chapter 3. To me, yeah, the limits are important for understanding the rest. Look at this one, 11 sections. Are we going to have time for 11? Probably not, but let's do as many as we can. We'll do the important ones and maybe skim through a few of them. Not saying they're not important. Time-wise, we have issues. Okay, let's get the slideshow set up for them. Current slide. Okay, yeah. Are y'all aware of what this is a picture of? I think.
Jet going into or breaking the sound barrier?
Absolutely. A jet plane breaking the sound barrier, just like Rodney getting here early, okay? Yeah, okay, just kidding. All right. Perfect attendance, by the way, folks. Ding, 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 ding. Way to go. Okay. Let me see if I can clean this up a little. I should be able to do better than that. Okay. Yeah, this is a plane breaking the sound barrier. I've seen a little bit neater pictures than this, but still, this is pretty good. To catch this just perfectly like that. But I've seen the picture where you have almost a perfect cone here that he's popping through. What's happening there, of course, sound travels at a finite speed. And this plane has approached and then exceeded that speed, which what that means is that the sound waves moving ahead of the plane, as he speeds up, as long as he's below in subsonic speed, the sound waves are preceding him. But the closer he gets to it, sound is a pressure wave, and you're pressing all those air molecules together, including the moisture that's in the air, and pressing them together forms a little cloud. Now, what I can tell by this picture, it's not a very moist day. This may be over a desert. There's just not a lot of clouds there. Pick a fairly clear day in the southeast. You know there's always moisture in the air, just about always, and he'll go through a perfect little cone. But what he's doing is push together all those things, and then when he finally breaks it, he's actually going faster than the waves do, and that's why he's breaking through the cloud. He's actually breaking through that compressed layer of water molecule droplets that were in the air, formed his own cloud there, and then broke through that cloud. Pretty clear. Calculus is the foundation for our understanding of motion, including the aerodynamic principles that made supersonic flight possible. Okay? So I'll leave it like that. This is interesting the way it's stated, including the aerodynamic principles that made supersonic flight possible. What are some aerodynamic principles that make supersonic flight possible? Say again? Okay, I can't quite get it.
You're talking about like the kinetic and the potential energy?
Okay, yeah, all those are involved with it. Here's the key, what I'm getting at. Notice aerodynamic. What do you think of then? Slick. Notice there's no boxiness like a car has or something like that. The windshield goes up like this, like what are those box cars? Yeah, that's not going to work. Okay. What you're trying to do is allow the air to flow smoothly. Now you have a little bump here where the cockpit is. You got to. You got to see out of it. And notice he has a little cloud behind it because that drug some of that with it because that isn't very as aerodynamic as the rest of it. But notice the whole shape of everything here is so smooth, and so you're minimizing your air resistance is basically what you're doing. If you didn't have things to do that, you're going to have a hard time getting fast enough because you get so much friction from the air resistance. You might think air has that much resistance. It does. I can remember as a little kid, we never had air conditioning in our cars. And we lived in Georgia, which is pretty hot. So in the summertime, the windows were down, okay? Especially with 6 of us in that little car, okay? And if I was sitting by a window, I'd love to put my hand out and feel it do. But now, if you're going at a slow speed, I could do that, and I get some of the air to deflect in on me. That's why I did it. Of course, I like having it out there too when my dad wasn't looking. But if it was at a rapid speed, you could almost dislocate your shoulder because, yeah, the air has, and that car's not going anywhere close as fast as that. So, yeah, he's not going to put his hand out the window to see how it feels. Okay, no, he isn't. He doesn't have a window. Okay. He has a window, but it won't open. Okay, too much on that. All right. Now, differential calculus. Not all of you have books. Do you yet? Okay. Differential calculus is the study of the derivative. Differentiation is the process of computing derivatives. What is a derivative anyway? Okay. In fact, back in the financial crisis, one of the things that were blamed for this was these people who were banking on derivatives. When I first heard the concept of derivatives, I said, finally, those Wall Street people are beginning to make sense. They studied the rates of change. I thought they were really using derivatives. I thought, smart move. And I found out they're talking about something completely different. Dumb. Okay. So what is a derivative? It's how a function is changing relative to the variable, basically, is what you're getting at. A derivative is a rate of change. Another definition is the slope of a tangent line. Or more formally, the limit of a difference quotient. Remember difference quotients from 112? Change of f over change of x. Okay? The limit of a difference quotient as we'll explain shortly. In this chapter, we explore three facets of the derivative, develop the basic rules for differentiation. When you master these techniques, you'll possess one of the most useful, flexible tools in mathematics has to offer. And first of this chapter, we're going to be focusing still on those those limits, okay? And after a while, you're going to learn the rules for differentiation, and you almost never have to go back to those limits again, okay? But here's what we've got. Begin with two questions. What is the precise definition of a tangent line? Okay? We'll deal with that in just a minute. And how can we compute its slope? To answer those questions, let's return to the relationship between a tangent and secant lines first mentioned back in 2.1. We've already done this. The secant line through two distinct points, P, A, f of A, and Q, x, f of x, strange there, on the graph of function f has a slope. Okay? We'll get to that in a minute. Okay? Let's go back to the difference quotient. Difference quotient is difference in f over difference in x, the quotient of the two. Difference, two differences, one divided by the other. That's what a difference quotient is. That's f of x minus f of a, say, over x minus a. Okay? F of x plus delta, x plus h minus f of x over x minus h minus a. In other words, over h. So it's a difference between, it's the quotient between the difference of the function values and the difference of the independent variables. Okay? Now, this is what they were talking about. They got the verbiage ahead of their graphs, so let's zoom in on this. I think we can get it all in one slide here. Okay. Here's your secant line. We did this before. Here's your point at P, which is A on the x-axis. That's your x value. F of A is your y value. Okay? Whatever that function operating on this A gives you that value on y. Okay? Then you go up here to x. Here's your x. There's your f of x. Okay? Whatever that value is. Now, what's the difference between those? F of x minus f of a. That's your change of f. Your delta y. Change of y, whatever you want to call that. And here's your delta x, which is x minus a. How much has the x value changed? How much the y value changed, the quotient of that with the x value. How much of this does per unit that? Okay? That's the same limit we just saw. Delta f over delta x is f of x minus a over x minus a. F of x minus f of a over f of x over x minus a. I can't get it right. That's your slope of this secant line going between these 2 points. So remember what we did in section 2.1 or 2, wherever we were back there. We let this point get closer and closer to this point. So if it came down here, the secant line, down here, the secant line was a little bit less steep. And when it came down here, a little bit less steep. And then it came down here, a little bit less steep. Down here, until finally you coalesce the two on top of each other. That gave you the tangent line. Okay? So the slope of the tangent line is the limit of the slope of the secant line as x is approaching a. Okay? X getting closer and closer to a. That's what we mean, and that's what a derivative is. The slope of that tangent line. The delta f over delta x, that's a finite difference there. That's your slope of the secant line. Later we'll give this a name. It'll be df over df dx, and that will be the slope of the tangent line. Okay? So that's what we're doing. Our goal is to compute that slope. I just sort of gave it away. It's the limit of this one as x is approaching a. Okay? Does that sort of make sense? Yeah, not? Okay. Any questions about it? Okay. This, I think, says the same thing. Here you got your P and your Q, the Q with the X and the P with the A, and now you're letting this X creep in toward the A here. Okay, well, let's see if we can blow this up first. Wait a minute. What happened to my previous slide? Okay. This is the one I wanted to blow up. It just disappeared on me. Okay, I can't get but, let's just do 2 at a time. Okay, we'll start with this one. Here's your A and there's your X. Okay, here's your curve. And what you do, the slope of that secant line is y2 over y1. That's this value over this value, f of x minus f of a, divided by the change of x minus a. That's your delta f over delta x. Okay? Now, what we're going to do is let the f value, the x value, get closer to a. And you see this has a slope here. This slope has decreased ever so slightly, but it's still in the same general ballpark. F of x, this value, minus f of a, divided by x minus a. The change of y with change of x, slope of the secant line. Okay? But we're going to let that x get just a little closer here in C. Okay? Let that x get a little bit closer to a. That's going to bring down the f of x closer to f of p, or f of a at p. So now that slope is decreasing, in this case, decreasing a little bit more as those are getting closer together. And what's happening? The changes of f's are getting smaller, but the changes of x are getting smaller. Okay? Okay, so far, until we keep getting closer, until ultimately the Q lands on top of the P. Now, what's the problem there? Your delta y's have gone to 0, and your delta x's is also gone to 0, because x is equal to a. And you can't really take that limit that way. You can't take the limit. You can't evaluate it. You can evaluate all these slopes, but you can't evaluate that one unless you go to the limit. And that's exactly what we're going to do. Okay? Does that make sense? Kind of. Sort of. A little bit. Okay. Now, based on this intuition, they say, we define the derivative and we give it a couple of names. There's different notations. Don't let the notations mess with your head. But one of these expressions for a derivative is f prime of x. Now, why they start with this one, I don't know. I would start with the ones that are more similar to what we have been doing, and then say, okay, and we also call this f prime. But there they're starting with the f prime, which is the most distant from what we've been doing, and then going to give it another name. And it's f prime, and by the way, they're saying at the point A, not at x. You could talk about f prime of x in general, but we're looking for at the point A, when x is equal to A. Okay, so what would that be? F prime of x, and why they give you that form, I'm not sure, but it's fine. The limit as x is approaching A of your f of x minus f of A over x minus A. Okay? Now, according to our pictures there, as Q gets closer and closer to P, of course your change of f's are getting smaller. That's going to 0. And of course the change of x's are getting smaller too. X is approaching A, that's going to 0. So you have what you call an indeterminate form. 0 over 0, just like we talked about before. You can't plug in A, but you have to calculate what that derivative is. Now, They say that, but they give you a picture that has something else in it. This time, rather than talking about x itself, we're going to let x be a plus h. Okay? X is a plus h. And the rest of it's the same. Alpha of x minus alpha of a is alpha of a plus a minus alpha of a. And now the difference between a and x, difference here is a plus h minus a. H go out, this is h. So basically what you're doing is letting the h get closer to 0 as this function difference get closer to 0. Also, what's that slope of that? You had to find that. Okay? That's what we're getting at. So that's another way to express a derivative. Again, they're kind of mixing their messages on you. Here's the other way you can do it. Using this x equal a plus h, you can also say that this thing here is f of a plus h, that's your x, minus f of a, that stays the same, over your x is a plus h minus a, just like that stays the same. These go out, and this is the same as f a plus h minus f of a over h. That is also a difference quotient, and the limit of this, now your limit is as h is approaching 0. As h is getting smaller, 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 this is also a definition of f prime of a. Okay? Now, so those are two ways of writing the same thing. Let x approach a or let h approach 0. Saying the same thing. So here are those two, your definition of an integral, of a derivative, sorry. I'll get into the next course yet. The derivative of f at x equal a is the limit of the difference quotient if it exists. Okay? Now, if this difference was not going to 0, that one was, then you'd have some number over 0. That doesn't exist. Okay? There may be some where this is going to 0 and that's going to 0 that also may not exist. But we're going to be dealing mostly with those that do. Okay, so here's one way to express it. F prime of a, the derivative of alpha a, is the limit as h approaches 0 of alpha of a plus h minus alpha of a over h. This differs from a by h units. This is at a, so that's a y difference. And then the difference between this a and a plus h and a is just h. H is getting closer and closer to 0. When that limit exists, we say that f is differentiable at x equal a. An equivalent definition would be, this is the first one we had, f prime of a would be the limit as x approaches a, f of x minus f of a, again a difference quotient divided by x minus a. It's the same thing, just as this one has x equals a plus h. Okay, so either one of those works as your definition of a derivative. All right. Now, go and take a little visit to nostalgia, okay? Probably shouldn't have blown that up yet. The tangent line. Let's assume that f is a differentiable function. We've only given a definition. We haven't said how to do it exactly, except taking a limit. We say it is differentiable at x equal a. The tangent line to the graph at x, y equal f of x, at the point P, which is a f of a, is the line through P of a slope f prime. Your derivative is your slope at a, and the equation of that tangent line, if you remember from your point slope formula. Do you remember those? It was basically y minus y0 is equal to m times x minus x0. Does that ring a bell, or is that way distant past? let's do a little reminiscing then, okay? If we have a line here, now that happens to be a tangent line, we don't know it yet, but that's a line. How would you determine the slope of that line? If you had 2 points on the line, how would you do the slope of it? This point is x1, y1. This point is x2, y2. What would be the slope of that line? Remember the symbol we used for slope? M. M is equal to y2 minus y1 over x2 minus x1. And guess what? It didn't matter which one you named 1 and 2. If you moved them around, that would just be the negative. Negative or negative is still the same. I mean, it doesn't matter. Okay. That's your slope formula. We remember that pretty well, don't we? By the way, what we call this is delta y over delta x. There's those deltas again. Those are the capital deltas here now. Okay. Now, what I'm going to do is multiply both sides of this equation by x2 minus x1. Okay? And here these go out. I'm going to flip sides too and make this y2 minus y1 is equal to m, I'm reversing the order here too, x2 minus x1. That's that same formula, it's just written with the denominator multiplied by the other side. By that? Now this is if you have the 2 points, you know their coordinates, and you're calculating the slope. Now I'm going to pull a sleight of hand on you. Now I'm going to say you know the slope, and you know 1 point. This will give you the equation of the line that goes through that point at that slope. And here's how I do it. Watch this sleight of hand. I'm going to take my little pen here and erase the 2's. Okay? What that gives you is an equation for a line. Equation in the variables x and y, those are not points anymore, those are variables. Your m now was the thing you didn't know before, now we do know it. Assume that we know the m. Okay? So, let's get back to what we're talking about. Your y1, when x is equal to a, y1 is f of a, right? So we're going to rename that a little bit. And the slope, as we just saw, was your f prime at a. The slope is the derivative of the function at the point a. And when you plug those things in, you get y minus f of a is equal to f prime of a times x minus a, and that's exactly what we've got here. Okay? It's just the point slope formula, with the point being a f of a and the slope being f prime of a. The slope at the value of the tangent line at that point a. Okay? So this is nothing really all that new if you just think back and relate it to what you've known before. Okay? I think we're ready for example 1. Let's see, do we? Yes, I think we have a thing for example 1 here. Find an equation of the tangent line to the graph of f of x is equal to x squared at x equals 5. Okay? We want the equation of a tangent line. Now, an equation of a tangent line has got to have x in it and a y in it. Those are your variables. It's got to have an equal sign, otherwise it's not an equation. And you've got to have some slopes and some point. That's what you need, a point and slope. Now, what is your... This is the rough part. What is the derivative at x equals 5? Okay?
25.
Okay. That's the value. Okay. So
2x.
what you just said, f of 5 is equal to 25. That's right. What we want is the derivative of f at 5.
So 2x, would that be 10?
Okay. You already know how to take a derivative. Right. Okay. The others don't necessarily know that yet. Okay. So, but you're right. That is what it would be. We have to do it by that limit. We have to figure out what f prime of 5 is. Okay. Because your formula here is y minus f of 5 is equal to f prime of 5 times x minus 5. Okay? That's what we're trying to do. That's from the previous definition. We know what f of 5 is, you just told me. We know what x is, you just told me. Okay? We need to figure out what f prime is. Well, what? So far, all we've got is the limit. Okay, now, are they using h? No, they're using f. X approaches 5 of f of x minus f of 5 divided by x minus 5. Right? That's what your derivative is the limit as x approaches 5, f of x minus f of 5 minus x minus 5. And obviously that is a 0 over 0 indeterminate form, because as x is approaching 5, this is approaching alpha 5, okay? And alpha 5 minus alpha 5 is 0, and 5 minus 5 is 0, so yeah, you've got that. But we do know what f of x is, and we know what f of 5 is, so let's plug those in too. So this will be the limit as x approaches 5, and what's your f of x? X squared minus your alpha 5, 25, right? Divided by x minus 5. Can we take that limit? You can't just plug in. If you do, you get 0 over 0, indeterminate form. But what might be our next step?
Unfold it.
Yes. Factor that numerator. And how does it factor?
X plus 5, x minus 5.
And divide that by x minus 5, and look what happens. Those two go out, and now we can take the limit as x approaches 5 of x plus 5. That's all that's left. And what's that limit? Yo! You can do that, can't you? What is that? Is your 10. And that's what you said it was before. Okay? Now we have all the pieces we need. We have y minus 25 is equal to 10 times x minus 5. That is your equation of the tangent line. Now that's not the prettiest form of that. A little bit nicer to get it in what we call slope-intercept form. So we can do that too. That'd be y minus 25 is equal to, distribute the 10 across, and what does that give you? (10x). Second, minus 50. And then we're going to add 25 to both sides. And that gives you y is equal to, because that goes to 0, 10x minus 25. There you have it. There's your equation of the tangent line. Actually, that form up there is just as good. This is it in slope-intercept form. If you want it in what they used to call standard form, you could say that's 10x minus y is equal to 25. There's another. That's what they used to call standard form for a line, but it's really sort of a useless form. So I don't usually write it, but I just did. There's many ways you can write the equation of the tangent line. All three of those are correct. That's why, if we were using one of those computerized software packages to assign homework and stuff in, you might give me one, or do one of those, get an answer, and then the problem would say, that's not the right answer. When it would be the right answer, but they're just looking for a different form of the answer. So that's why I don't like using those. One reason anyway. Okay, let's see what they got wound up with. Do they ever give the equation of the tangent line? I'm not seeing it, do you? They talk all around it. Oh, there it is at the bottom of the page. They write it in both of the first two forms. Y minus 25 is equal to 10 times x minus 5. And in slope-intercept form, it's y is equal to 10x minus 25. There it is. And that's what they have right here too. Y is equal to 10x minus 25. Make sense? Now, a little side blurb here before we get too carried away here. Isaac Newton referred to calculus as the method of fluxions. Now, I'm not sure what that means. It says it's from the Latin word to flow. Flux, yeah, I'm used to that word. Flux, flow. In physics, when you're talking about electrical fields, you get into the concept of flux. Okay? Even though there's nothing really flowing. Huh?
We're doing that now.
Yeah, fantastic. Okay. In terms of differential calculus, but the term differential calculus introduced the Latin form for calculus differentialis, and that was Gottfried Leibniz, I don't know how you pronounce his name. That eventually won out and was adopted universally. Okay. They thought about it for years, wasting a lot of time and effort, but they did. So there's two names you could write about, or their terminology, or, there's lots of things you could write there. I just pointed that out for that. Now, example 2, I don't think has a slide. I think that is for example 3. So let's go back to this and erase everything on the slide, and we'll do example 2. Not this picture. So not that picture, but we'll do example 2. Compute f prime of 3, where f of x is equal to x squared minus 8x. Okay? What do you reckon that definition is for f prime of 3? Go back a box or two and you'll get one of two definitions for it. Definition of a derivative at a point. It's a limit. That's the limit as x is approaching what?
0.
No? 3. Okay? Of f of x minus do that equation 2 on the previous page.
F of A.
F, and your a here is?
Negative 8x.
No. A is 3. Okay. Okay. Divided by change of y over change of x. What would be your x?
So
X minus 3. You got it. Feel like a dentist. Okay. All right. Now, we got a little bit of calculation to do. Not too bad. We already know what f of x is. We just don't know what f of 3 is. So let's do that next. F of 3 would be what? No limit. Just f. Plug it in. Just like Glade. 9, 24, which is negative 15. Okay. So what we have here is, I'm going to forget about the limit. I'll bring it back later. F of x, which we have, x squared minus 8x minus f of 3, which is negative 15. So that's plus 15, right? Minus and minus is plus. Divided by x minus 3. Now, what's our only hope here? Not our only hope, but a hope.
Getting that x out of the denominator.
Yeah, we need to get we can't have x approaching 3 with that in the
So we need
denominator.
to factor the top.
Okay, we're hoping we can factor the top. And we're hoping we can factor it, but not only that, we're hoping we know what one of the factors is, don't we?
Yeah, x minus 3.
We hope one of them's going to be x minus 3. What would that make the other one have to be?
X plus 12.
Minus 5, right? It would have to be,
Never
right?
mind, yeah.
Okay, let's see if that works.
No,
We're hoping. Let's see if it does. X times x is
x squared.
x squared. That works. X times a minus 5 is minus 5x.
Yeah.
Minus 3x, sure enough, is minus 8x, and plus 15, yes, that's the way it factored. We were hoping it would that way, okay? I cheated on it, but you see how? Okay. Now, what can we do, since that does factor that way? Divide out the x minus 3. Now let's impose our limit again. The limit as x approaches 3 of x minus 5. And what would that be? Wipe that out. Limit as that. Let me write it again. Limit as x approaches 3 of x minus 5 is equal to negative 2. Okay. I think we did it, didn't we? That is f prime of 3. Okay. Now, why in the world they go back to the a plus h one? I don't know. It worked perfectly fine the other way, but let's do it with a plus h since it seems like they're doing it that way. Okay? What is your a? 3, and the h is now your sort of like your x. It's not. It's okay. So we're going to do it this way. F prime of 3 would be the limit as h approaches 0 of f of a plus, 3 plus h. No reason to put the h in there. We've already identified it. So a is 3. So 3 plus h minus alpha of 3 over h. Okay? So now what we have to do, see why this is more difficult? We now have to plug in this here. So f of 3 plus h. We know what f of, well, we've already calculated what f of 3 is here. Okay? We already have that one done. But now we have to do f of 3 plus h. What is that? From here.
X squared minus.
Okay, but
Is that, oh,
you put in,
we're plugging
yeah,
that
plugging that, yeah.
everywhere. So 3 plus h squared.
Squared minus 8 times
3 plus h.
3 plus h. Okay? And what's 3 plus h squared?
H 9.
9
6h
plus 6h
and then h squared.
plus h squared. Very good. Minus 24
and then negative,
minus 8
8
h. Exactly. And that's your f of 3 plus h. We need to subtract from that f of 3, which is minus a minus 15. So that's plus 15. And then the denominator is going to be h. Right? All right, anything we can do to simplify that numerator, please say yes.
Yes.
Okay, what would that do? We can combine like terms, can't we? What do those add to?
0.
Oh yeah, that goes to 0. Nice. And
And then, so you're left with the 6h and the 8h can combine, and that's negative 2h.
okay, so let me do h squared minus 2h. Can I do it like that? Okay.
And then
Over h. Now what can we do?
Now we can factor the top.
Oh yes, we can. What does that factor?
Well, you take out an h.
Okay,
And then
that leaves you.
you're left with h minus 2.
Okay, over h, and then you can divide out the h's. Now that's what we're taking a limit of as h is approaching 0. That's our limit back here, and that would be negative 2,
Which is what we got with
which is what we got with
the other.
the other one. Okay, so both ways we get negative 2. Frankly, in this one, I kind of like the first way better. The book did it the second way, which I guess because it was hard. No, they wouldn't have done it for that reason, would they? Okay, but we got negative 2. Now, I hope y'all are having little flashbacks of Math 112 when you did difference quotients and you calculated them. We would get it down to something like this. What we didn't do was take a limit as h goes to 0. Just one more step. But we remember those fondly, don't we? Yeah, yes. All right, let's go to example 3. Sketch the graph of f of x is equal to 1 over x. Thank you very much for doing that for me. Now that's not the whole graph, though. If we were doing the whole graph, it would have extended the y value down here, y-axis down here, the x-axis over here, and then it would have been a piece like that as well. Okay, they didn't do it. We don't need to, and here's why. Sketch the graph of f of x equal 1 over x and the tangent line at x equal 2. So they're not looking at any negative x's. So that's why they left that out. Okay? So that's what we've got. Your f of x, I'm going to erase some stuff here if that's okay, because it's messing up with something I need to see. Here's your f of x, okay? So sketch the graph of that, they've done it, and the tangent line at x equal 2. Now they've sort of sketched it for us. I hate they did that, because we like to sketch it ourselves, don't we? Okay. Now based on the sketch, do you expect f prime of 2 to be positive or negative? Just looking at that tangent line there. Here's the place where x equal 2, here's the curve, y is f equal 1 over x equal 2, 2 is equal to, f is equal to 1 half. 1 over 2 would be 1 half. So here it is, 2, 1 half. There's the line, there's the tangent line there. Looking at that, would you expect it to be a positive or negative slope? Negative. So it's going downhill. Slowly, but it's going downhill. Okay? Now, it says find an equation for the tangent line at x equal 2. What are we going to need to do that? Say this again now. Okay. I can't quite hear what you're saying, but to get the equation of a tangent line, you tell me what that would be. Y minus, remember, go back one page, yeah, right there. Y minus what? F of 2. Yeah, because we got x equal 2. Y minus f of 2 is equal to the slope of the tangent line, which is f prime of 2. Remember, that's what we said. The first derivative of a function is the slope at that point. Okay? So there's your slope, and then you do x minus 2. Your variable y minus f of 2, your variable x minus 2, and your slope being f prime of 2. Okay? Now, I've already said it, but we didn't actually calculate it. What is your f of 2? I've already said what it was. Say again? 1 over 2. You got it. Okay, we got that. So now what we have to do, we've got this piece. We've got this piece. We need that piece. So, back to that previous one, f of f prime of 2. What is the definition for that? And there's one of two ways you can do it. I don't care. You tell me. Remember, the definition on the previous page, the middle of the page, gives you two ways to calculate it. You pick one of them. Let me know. Say again?
F prime of A equals the
Okay.
limit as
The limit of, as x approaches 2, of what?
F of 2 minus, I'm sorry, F of X.
Okay, f of x minus
F of 2
f of 2
over X
minus 2. Got it. So, a lot of ugliness here. Let's see if we can clean up a little bit of that. Okay, a little bit there. Okay, not quite as ugly as it was, but still not bad, not the greatest. Okay, so we first got to do that. Let's take it out of the limit for a moment and do that. We know what f of x is, right? We know what it is, right? 1 over x. We know what f of 2 is. 1 over 2 divided by x minus 2. So we've got some fiddling to do with that. What do you reckon the first string of your fiddle needs to be? What's messy about that? All the fractions are, well, no, be careful. Rodney loves fractions, so don't speak too badly of them. Okay. What could we do to simplify that fractional form in the numerator? Before you can subtract fractions, you have to have common denominator. What do you reckon the common denominator is of those two fractions? 2x. Okay. Now, what do you got to do to make this one a 2x? Multiply 2, but if you multiply the denominator by 2, you got to multiply the numerator by 2 too. Now, what you need to do to make that a 2x? Multiply by x. That means you multiply the numerator by x. So that now gives you 2 over 2x minus x over 2x over x minus 2. All right, we can still do something to combine those, right? We got the same denominators, so that's going to be 2x, and your numerator becomes 2 minus x. And that's all over x minus 2. Now, I'm going to rewrite that ever so slightly as 2 minus x over 2x times, or let's do it as divided by x minus 2, which would be 2 minus x over 2x times, no, let's not use that time sign, a dot, 1 over x minus 2, right? I don't know if you needed all that, but I showed it to you. Now, how are these two expressions related? They look similar, but not quite. Do you remember? They what?
Isn't it the commutative property?
There is something involved. What would you have to multiply one of them by to make it look like the other? What?
Oh, by a negative 1.
By negative 1. If you multiply.
It's a negative 2, and that's a positive 2.
Yes, multiply this by negative 1, and you'd have to multiply this by negative 1 too. But if you did that, then you would have here a minus 2 plus x over minus 2x times 1 over x minus 2. You don't have to go through all these steps. Rearrange that. That's x minus 2 over minus 2x times 1 over x minus 2. And guess what? Those go out, and you have, let's go back to your limit. F prime of 2 would be the limit as x approaches 2, and we've done just that thing here. And I'm going to pull the minus sign out in front, 1 over 2x. Okay? Can we take that limit? What is it? You got it. Okay, number 1, we saw it. We thought it wasn't a negative slope, and it is. And it's a very gradual negative slope. 1/4 is pretty gradual. So we almost have I think we have what we need. Here's our equation of the tangent line. Y minus, what was f of 2?
Or 1/2.
1/2 is equal to, what's f prime of 2? Negative 1/4 times x minus 2. Okay? Now again, it'd be nice to get rid of some of those denominators with it. So let's multiply everything on both sides by 4. Okay? So this becomes a 4 here. This becomes a 2 here, right? 1/2 of 4 would be 2. And this completely disappears. You got a minus sign still. So now what we have is 4y minus 2 is equal to minus x plus 2, right?
Which you should divide by 4.
Not yet.
Okay.
Let's add 2 to both sides. And you have 4y.
Oh, that's going to come out nice.
Oh, isn't it though?
Yeah.
Is equal to minus x plus 4. Then when you divide by 4, you get y is equal to minus 1/4 x. There's your slope. Plus 1. With a y-intercept of 1, and look where that line seems to be heading. Smack toward 1. So that makes me feel really warm and fuzzy. I think we got the equation of the tangent line. Sure looks good. And what's more, the point 2 1/2. Let's see if that's on there. You put a 2 in here, and what do you get?
1/8.
No, 2 is up here.
Would that not be negative 1/8?
Okay, the x is in the
That's right. It would be
Yes, 2.
negative 1/2.
negative 1/2 plus 1
Plus
is
1 is positive 1/2.
positive 1/2, and sure enough, that's positive
Yeah.
1/2. Yes.
Sorry.
Okay. You're really sorry. Okay. No, I'm sorry. You didn't say that, did I? Okay. All right. Let's see what they got. Oh, they used the 1 plus h's or 2 plus h's. It still works. I probably should have done that. I didn't look ahead. Okay.
Did it come out easier?
They came. Well, it's pay your money and take your choice. You've already paid your money, so you take your choice. If you want me to next time, ask me and I'll do it. You can try it at home with the 1 plus or 2 plus h. See what you get. It may actually be a little easier. It looks like it's not as much writing as we did, but I may have taken 2. We'll begin next time with the graph of a linear function on page 116. Let's see how far we got. Ooh, we made good progress on 3-1. Homework exercises here. Try number 1. Do number 1. Then I think you can do, and they ask you to do it 2 ways. So any of the odds 3 through 7. Okay? And then I would say choose either 9 or 11. I'll let you choose. And it's referring to figure 12, so I'll let you figure that one out. And let's just stop there. I'm not sure the next one is we'll do some more stuff to. I think you can do any of either 13 or 15. I think you can do it. Okay. And I think you could do either 17 or 19. I think you can do any of the odds 21 through 27. And I think you can do any of the odds 29 to 45. The more I look, the worse it, and let's see. I'll let you stop there. We'll pick up the rest of those next time. Okay. Good deal. We'll see you. Have a good weekend.
Yes.
But it's not a holiday weekend, is it?
See you Wednesday.
The weekend part, Monday. Yes. Okay. We'll be here Monday. Good deal. All right.